Thanks. Okay, well, first I want to thank the scientific committee for the acceptance of my talk about this work, which was recently submitted to Astronomy and Astrophysics, and is part of my PhD thesis. Lilia Bassino and Celeste Parisi are the directors of this thesis, and this work is part of a project in collaboration with the rest of the authors. So, first it's important to think about why we study the Small Magellanic Cloud.
Bruno, are you there? We're not hearing you.
Structure of hydrogen gas interpreted as, sorry?
Yeah, we lost you. There was a moment of silence, but yeah, now we can hear you.
I continue. Can I continue?
You can go ahead. We can hear you now.
Okay, thanks. They show a diffuse structure of hydrogen gas interpreted as the consequence of interaction between them and the Small Magellanic and Large Magellanic Cloud system with the Milky Way. The latest research based on the most accurate measurements of proper motion with the Hubble Space Telescope and Gaia and updated Large Magellanic Cloud and Milky Way mass estimates suggest that they are experiencing their first encounter with the Milky Way, with our galaxy. Also, the current morphology of the Small Magellanic Cloud could be the consequence of a recent collision between the Magellanic Clouds. In this scenario of interactions, the star formation history and chemical enrichment processes of the stellar population of a galaxy are, of course, affected, and their spatial, age, and metallicity distribution and gradients present distinctive effects of such interaction processes. So the Small Magellanic Cloud star clusters have proven historically to be excellent tracers of the chemical and dynamical history of this galaxy. In order to increase the number of inner Small Magellanic Cloud star clusters homogeneously studied with the calcium technique, we have observed 6 clusters in the inner region of the Small Magellanic Cloud, which are spatially distributed, as can be seen in this figure. We consider the inner region, this one inside 3.4 degrees. For each cluster, pre-images in the G and R filters had been previously obtained with the instrument GEMINI-S, from which the color magnitude diagrams were built. We selected red giant branch star from the color magnitude diagrams as our spectroscopic targets. And well, the spectroscopic data for the selected red giant branch stars consists of intermediate resolution near infrared spectra in the region of the 3 calcium triplet lines obtained with GMOS in mouse mode. It comprises more than 150 spectra of stars in the area of our Small Magellanic Cloud star cluster sample. In order to measure radial velocity of a program star, we cross-correlated or normalized spectra with red giant branch theoretical template taken from the library of Coelho. And for each target, we determine the metallicity by using the equivalent width of the 3 calcium triplet lines and the difference between G magnitude of the star and the magnitude of the cluster's horizontal branch or the red clamp. And we use the calibration of Diaz and Parisi 2020. So we consider as member star those targets located closer to the cluster center than the adopted radius, and having radial velocities and metallicities within the limits considered in each case. We adapted the cuts from our previous work, for example, Parisi et al. 2015 or 2022, and Diaz et al. 2021 and 2022. In order to perform a statistically more significant study of the Small Magellanic Cloud chemical history, we enlarged our sample by adding 51 clusters having calcium triplet metallicity, derived with the same method as in this work. So we obtained a final sample with 57 clusters. 37 of them are in the inner region. In order to analyze the existence of bimodality in the metallicity distribution, we apply the Gaussian mixture modeling test to the full sample and to the inner and outer regions. In the inner region, the metallicity distribution is more likely bimodal than unimodal, while in the whole sample and in the outer region, we obtain a lower probability of bimodality. Thus, we identified in the inner region two potential groups, one more metal poor and one more metal rich. We make clear that more metal rich and more metal poor than the mean Small Magellanic Cloud field metallicity, which is approximately -1 dex. We make clear that this region is defined with the projected distances to the Small Magellanic Cloud center, and we will need 3D distances to confirm it. However, these two potential groups have interesting chemical behaviors, as I will show in the next slides. We analyzed the metallicity gradient, and we obtained the result that we show in this figure. Field symbols are the cluster of this work. We found negative and positive gradient for the inner and outer region, respectively, which are the solid lines. And we perform a linear fit to the two internal groups separately, which are the dashed lines. Shielding, in this case, metallicity gradients close to 0 for both of them. Note the absence of clusters in the inner region with metallicity in approximately -1 dex, which doesn't occur in the outer region.
You have 2 minutes.
Thanks. In order to further analyze the chemical properties of the two potential inner cluster groups, we built the H-metallicity relation for the inner region and found that metal-rich and metal-poor clusters seem to follow different relations. Metal-rich ones show a subsequent chemical enrichment process which increase the metallicity considerably, at least for about half of the younger clusters, in agreement with the model proposed by Harris and Zariski in 2004 and Perren et al. In 2017. On the contrary, metal-poor clusters appear to not have undergone any chemical enrichment. While the nature and possible existence of the two potential groups need to be confirmed, if they do exist, we can speculate that the metal-rich group corresponds to clusters formed in situ, while those of the metal-poor group have a different origin Then the H metallicity relation of the Small Magellanic Cloud main body corresponds to the relationship found for the metal-rich group. So as a conclusion, we can say that we find a high probability, 95%, that the cluster metallicity distribution is bimodal in the inner region, but unimodal in the outer region. Then we found two groups that correspond to metal poor and metal rich cluster in the inner region. The cluster metallicity gradient is negative, but with a large error due to cluster metallicity dispersion in the inner region, but positive or null in the outer region. However, a linear fit for the metal-rich and metal-poor clusters separately are consistent with no metallicity gradient. And the H metallicity relation in the inner region show that the metal-rich clusters appear to follow the chemical enrichment of field stars given by Harris and Zaritsky, or the model proposed by Perrin et al. But metal-poor clusters do not present any chemical enrichment. So, our next objective is to determine 3D distances of our cluster sample to confirm our results and to analyze their orbits to determine the possible origin of each group of cluster. So, thank you very much.
Thank you, Bruno. Questions from the audience here or from the chat? While people may be actually thinking about ideas and questions and comments, Bruno, I'm not from the area, but I'm trying to connect this with what I know about the bimodality in globular clusters in galaxies, and the idea that they may be the result of interactions. That you may have like a first set of global clusters that were associated to a more the origin of the galaxies, or more at the beginning, and then you have some interactions that led to the formation of a new populations. Is it the idea that the younger population that the metal poor population that you're observing may be associated to a younger population that was triggered by the interaction with our galaxy?
Yes, if we assume the existence of two groups of cluster with different origins in the inner region, then we can speculate with in various ways. For example, we can think that metal-rich clusters have formed in situ while the metal-poor cluster were accreted, as observed in elliptical galaxies. Or we can think that metal-poor and metal-rich gas form a cluster in the inner Small Magellanic Cloud, whereas gas with intermediate metallicity form cluster in the Small Magellanic Cloud outskirts, or that the Small Magellanic Cloud experience infalls of gas with different metallicities, combined with inhomogeneous mixing of gas since its formation. And while the multiple encounters with the Large Magellanic Cloud would have triggered cluster formation by shock. But well, in all of this case, we need more information to be more precise with the origins of the two groups.
3D positions will help you with that then.
Sorry?
The 3D position with respect to the
yes,
center.
and the 3D distances are really important to really confirm the limits of this region that we define as the inner region or the main body of the Small Magellanic Cloud.
And actually, what I was telling you about the bimodality, there have been a lot of issues, but it's because dust has something to do with it, but it's just based on photometry. You have the spectra, so obviously you have a better look into this. So thank you. So let's thank the speaker again.